Welcome to the executive summary of the Ariadne study exploring the use of molecular dynamics simulations for high-performance space debris collision modeling. This study was conducted by Pablo Gomez from the Advanced Concept team at ESA and myself, Fabio Gradl. I'm a PhD candidate at the Technical University of Munich at the Chair for Scientific Computing of Professor Bungartz. When talking about space debris, there's no way of not mentioning the annual Space Environment Report by ESA. So this is one of the images of the report that I guess everybody knows. Over the first 50 or so years, there's not too much happening in terms of payloads. However, over the last few years, we see a dramatic increase in the number of payloads to LEO. So for new satellites, it's critical to ensure the long-term viability of their orbit. And this can be done through high-fidelity simulations. However, this orbit has some particularities to it that are hard to simulate. For example, there are many forces or perturbations which influence the orbit, and objects are moving very rapidly with 7 to 8 kilometers per second, which is quite a lot when you consider that our simulation box is typically only 20,000 or so kilometers wide. So what are the challenges unique to long-term small debris simulations? We have these high discrepancies in temporal and spatial resolution where we want to simulate years and years of population evolution in a simulation box that is thousands and thousands of kilometers wide. But at the same time, we want to catch exact moments of collisions of objects which are only meters or even small centimeters wide. The next point is that simulation of tens or hundreds of thousands of particles is simply speaking computationally costly. And because all of this long-term modeling of these simulations has been done with stochastic rather than deterministic models. And exactly this point should be tackled by this Ariadne study. All of the above are problems typically also encountered in particle simulations. Therefore, we wanted to build a scalable, non-stochastic simulation by exploring recent algorithms and tools from the particle simulations community. And we wanted to do this in a modern and sustainable way by using modern C++ and high-performance computing via a hybrid of OpenMP and MPI. In order to achieve this Ariadne study brings together a collaboration of the Advanced Concept team with their expertise in interdisciplinary projects, the Space Debris Office, which obviously has highly relevant domain knowledge, and our chair at the Technical University of Munich, where we have a long history of working on high-performance computing and particle simulations, especially molecular dynamics simulations. So what are the specific objectives of the study? First of all, we want to investigate the feasibility of deterministic conjunction modeling for long-term simulations. When this could be demonstrated, we wanted to see the potential for scaling this up with HPC technology, so that we ideally could simulate hundreds of thousands of small debris objects. And, as said previously, we want our tools to be usable beyond the study, so everything we develop is accessible and open source. With these objectives in mind, here are our core findings. The most important one first, it is definitely feasible to simulate a large small debris population over many, many years in a non-stochastic fashion. So for 600,000 particles, we could demonstrate a factor of 50 times real-time on just 128 compute nodes on a cluster with 8-year-old CPUs. Further, we saw that smart MPI domain decomposition is key, more on that however in the technical presentation. Using a sub-time-step conjunction detection algorithm greatly helped us with achieving the required accuracy while maintaining the speed of your simulation. And finally, a highly parallel and precise propagator is required to also keep up with the speed requirements. One of our objectives was to produce sustainable software, so we want to talk about these outcomes as well. First, we have our large-scale deterministic debris simulation, or short LADS. It's built in a highly modular fashion, meaning one can easily replace the propagator, breakup models, MPI algorithm, and so on and so forth. In the technical presentation, we show that this software scales to at least thousands of compute cores. It's completely open source, available in GitHub, and written in C++17. The second important software outcome is our modern C++ implementation of the NASA breakup model. It is validated against the original as well as other implementations that are available on the internet. It has a flexible API and is directly integrated into LADS as an optional module. And, as well as LADS, it is open source and available in GitHub and already in use by a group at MIT. Here, on the right-hand side, you can see a visualization of a small breakup simulation with LADS using the NASA breakup model. So overall, we can declare that all of our study objectives have been achieved. This project being a scientific cooperation, we also have noteworthy publication outcomes as well. First and foremost, our proof of concept paper presented at the ICSSA conference earlier this year. Next, we had 3 student projects working on different aspects of the simulation, doing a great job in pushing the project even further than we could on our own. And finally, there will be a paper about the scalability of LADs, but this is still work in progress. Until now, I have told you what we have achieved, but there's a lot more what we could explore. As we see it, one of the most beneficial aspects of LADs is its modularity. It allows for direct comparison of different algorithms or models, like breakup models or the cubes approach. One would only have to exchange a module in the code and could run the same simulation again and directly see the impact of these changes. The same comparisons could also be done for datasets, as we've seen that they also have a significant impact on the simulation. Furthermore, we would be interested in integrating the high-fidelity propagator Heyoka, or to investigate the impact of planned megaconstellations on the debris environment. But all of these are potential plans for the future. For now, we're at the end of the executive summary and want to thank you for your attention.